Greetings, A-level chemists. Here we've got another buffers question. So, it looks like a hefty question actually. Let's go through it. So, we're making a buffer this time by taking some solid pellets of potassium hydroxide and adding them to a solution of butanoic acid. Okay, cool. What we're going to do is we're going to write out the chemical reaction that occurs between butanoic acid and KOH. So, butanoic acid is this C3H7COOH plus KOH. So we're going to be making the buffer in situ again. So I am going to get some potassium butanoate and H2O. All right. Let's take that and see where we go next. So let's work in moles. So do I know the number of moles of KOH? No, but I can work it out because I have the mass over the molar mass, and the mass is 3.40, and the molar mass is going to be 39 plus 16 plus 1. So that gives us 56. So let's process that. So 3.40 over 56 is 0.0607 mole of KOH. All right, where do we go next? Well, next I can work out the number of moles of butanoic acid because I know the concentration and volume, and remember the number of moles is equal to the volume in decimeters cubed times the concentration. So what do we get? So 0.25 times 0.378. So we get 0.0945 mole of the butanoic acid. Just going to call it HA in my label, okay? All right, so now what I'm going to do is take those values and just put them into what I'm going to call an ice table. It's not, but these are my initial number of moles, okay? So just going to make a little table. It's going to help us in picturing what's going on. So do I know the number of moles of the butanoic acid? Yes, I worked it out. So I'm just going to put that under the butanoic acid, obviously. So the KOH, I've also got the number of moles for. Remember, I don't have any of this to start with because I haven't actually mixed the reactants together. Okay, where do we go next? So that's my number of moles initially. Now, when these react, before we figure that out, let's work out what's the limiting reactant. Let's work out what's in excess. So my KOH is a limiting because it's a 1-to-1 and there are fewer moles of it. So if that's my limiting, then my butanoic acid is clearly in excess. So let's just label these guys, okay? So how does that help us? Well, the limiting reactant determines how much of the reactants react and how much product is made. So this is going to go down by 0.0607, and this is going to go down by the same amount. Okay, consequently, my conjugate base, my salt of the acid, is going to go up by 0.0607. Okay, so we need a new column heading, and that is number of moles left over after they react. Well, I've got none of the KOH left, and because I've got no moles of the KOH left, I have excess acid left over. So remember, now I have to work off Ka. I can't use Kw expression. All right, so let's just process this. So 0.0945 take away 0.0607, and that gives me the number of moles left over, which is 0.0338 mole. That's the number of moles of weak acid left over. Okay, well, the number of moles of potassium salt that we're making is 0 plus this number, so therefore 0.0607 mole. Okay, now, where do we go next? We could convert to concentration. We probably should convert to concentration, but let's do it. Let's be good. It's an extra step, and the volume terms will actually cancel out, but it's good practice. So we're just going to divide through by the total volume, which is 250, and the question tells us, assume that the total volume of the solution remains constant at 250. So we're just going to divide these by the total volume to get the concentrations. Okay, so we're going to divide by 0.25 to get 0.1352 moles per decimeter cubed of the weak acid and 0.0607 divided by 0.25 to get 0.2428 as a concentration of the potassium salt. Okay, cool. So now we're in business, kind of. There's one more calculation that I need to do, and that is in this part of the question. Now it tells me what the pH is of the buffer. So if it tells me what the pH of the buffer is, I can convert that, because 10 to the power of minus pH gives me the hydrogen ion concentration. So 10 to the power of minus 5.07 equals, let's just process that. So shift log minus 5.07, and we get hydrogen ion concentration of 8.511 times 10 to the minus 6 moles per decimeter cubed. All right, so that's the grunt work. Where do we go from here? So let's write out our expression for Ka for the weak acid. So this is going to be C3H7 COO minus H plus all over C3H7 COOH. Okay, now let's think about what we know. And I'll try and color code this, okay? Well, I know, let's do it in red. Actually, let's use yellow. So I know the concentration of my weak acid. So that is in yellow. Do I know the concentration of my sodium salt? Yes. It's here. So these guys match up. Okay, well, what don't I know? Well, I don't know Ka, but there is one more term, and do I know that term? And that is the H+. Well, yeah, I do know H+, because, I'm not going to do blue on blue, but there you go. I just worked it out. So I know all of the terms for the expression for Ka. Now what do? Just plug them into the equation. So just make sure you get the order right. So 0.2428 times 8.511 times 10 to the minus 6 all over that in yellow, which is 0.1352, and that should give me Ka. So let's go through it. I'm going to multiply that number by 0.2428. Bingo. And then divide that through by 0.1352. Bosh. Okay, so that's my value for Ka for butanoic acid, 1.53 times 10 to the minus 5. Okay, and the units here are moles per decimeter cubed. Because that is moles per decimeter cubed, that is moles per decimeter cubed, they cancel out, and so you're just left with Ka as moles per decimeter cubed. Nice question, I like it. Hope that was helpful. Bye bye.